Hello everybody and welcome to our second part of our webinar series Make It Easy, brought to you by Sparasoft. Today we're having a relaxed view of functional safety in ADAS. My name is Vlad Grădinaru. I'm a principal safety engineer in Sparasoft Romania, and today I'm going to share about my experience so far in functional safety. I have 9 years in the field and I've seen a lot, but there are a lot of things to be seen. Our presentation today is structured like this. First, I will try to explain you why do we need functional safety. Second part, to explain you about how we go from idea to ASIL. Third part would be about requirements. Fourth, about architecture. Fifth, about verification. And the last part would be about safety culture. So, first things first, why do we need functional safety? Humans are using tools where in their daily activities, and those tools are either simple or complex, and they are meant to achieve their purposes. Each tool, simple or complex, has its own functionality or multiple functionalities. But we need to make sure that these functionalities do not result in harm to humans when they are malfunctioning. So for this we need to analyze it for the potential of causing hazards to humans if a failure that affects them occurs. So about this, functional safety ensures that if a failure occurs in a system, in an E system to be more precise, electric or electronic system in automotive, the risk that the functionality works incorrectly and causes hazards to humans is either minimized or removed. So the goal is not necessarily to remove the danger, unless we know for sure that it can be removed, but also to minimize its effects. The common view is that applying a standard is more bureaucracy. So in the end, people are saying, oh no, not again, applying standard for quality, for functional safety, for this, for that. But the truth is that the standard, it's not just a standard is not just something that adds more burden to your work, but actually it is a guideline compiled by the best people in the industry based on their experience, to make sure that you develop a good quality product, a safe product in the end. And it doesn't hinder innovation, but rather forces you to find new ways to improve the situation. A standard should cover all relevant stages in the product lifetime, when starting from an idea, moving on to the development, production, use, and decommissioning. So basically in automotive industry we need to cover everything. If you have an idea for a functionality, then you need to analyze it to make sure that it doesn't bring any hazard to humans. If it brings hazard to humans, then it has a safety relevance in this context, and then it needs to be treated accordingly during development stages, verification and validation stages, and then to the production when it is put in use in the field, in a vehicle, and then when it is decommissioned. The standard for functional safety in the automotive industry is ISO 26262, which is currently at the second edition, which was released in December 2018. And it looks like this. It has a V cycle. It is based on a V cycle. And as you can see, smaller V cycles for hardware and software development. On the left side, we start from the concept phase. We have the development, the requirements, the architectural design. And on the right side, we have the verification and validation of the product, and then send it to production, operation, and service and decommissioning. There are other parts which cannot be allocated to the V cycle, like supporting processes and safety analysis. My experience in these 9 years in functional safety in ADAS lies in the product development at the system level, with forays in the hardware and software development, and in the concept phase. I also am familiar with supporting processes and the safety-oriented analysis. So how do we go from idea to ASIL? Because first, you define a functionality. And where do we start? You have an item that you define it, and we have a functionality that you want to introduce it at the vehicle level. And then you make use of you have different sub-functionalities, and you make use of different components that when are put together are building that item and that functionality. And in this case, I took the example of autonomous emergency braking, where we have, as you can see, as an example, we have perception system that detects the environment, be it a camera, radar or LiDAR. we have a main vehicle ECU which collects all the information from different ECUs which are involved in this item definition. From steering system, for example, from the stability system, from the engine, and from the driver, through the driver vehicle interaction, which is done through the HMI. The driver itself, it's also part of the item. So we're not talking about E-system, but we also need to take into consideration the driver, because the driver itself interacts with the system, and its interactions with the system can trigger different reactions, and we need to make sure that those reactions are known to the driver and also do not introduce elements of surprise in our system. Everything here is going to an actuator, in which in this case it's a braking system. So in the end, we're detecting the environment, the main vehicle ECU analyzes the information, and then it sends, if everything is plausible and we do not cause any problems, it sends the command to the actuator, to the braking system to put the brakes. Now, how do we know how safe we need to be? First, we have the item definition. Once it is sufficiently mature, we trigger a hazard analysis and risk assessment, which in short is HARA. And in that HARA, the first step is to identify all possible hazardous events that can result from the malfunctioning behavior of the item that I showed you before, in certain operational situations and operating modes of the vehicle and their consequences. The most important thing that hazards shall be defined at vehicle level. So in this first step, we don't go, if we have knowledge about different ECUs that are parts of the item, we don't go in that depth, in that detail. We treat them as black boxes, and first we need to understand how a certain malfunction can cause hazards at the vehicle level. The level of detail for operational situations, because here we are talking, for example, about driving on highway when the sun is up, or when the sun rises, or when the sun sets, when it is rainy. So there are different combinations, but we need to make sure that we do not define those operational situations in too much detail, because we are risking to reduce the ASIL in the end to a lower level, which is not desirable. Why? Because if we say, for example, driving on highway, and we consider it driving on highway regardless of the conditions, then it will have a certain exposure. But if we're talking about driving on a highway when the sun sets or the sun rises, then the exposure will be less. Exposure, we will see a little bit later what it means. Second step is to classify all hazardous events with respect to three factors. One of them I mentioned, it's the exposure, which is the probability of exposure, and it addresses the operational situation. Severity, which it addresses the harm that a certain malfunction or hazardous events has on people, the driver, the passengers, and other traffic participants. And the controllability. If the classification according to these three factors is hard to make, then try to be as conservative as possible. Go with the worst case values. Why? Because it's better to consider a situation that is more dangerous than in reality, than to think of it that it's more safe and then not taking the necessary measures. A third step is to determine the ASIL. ASIL stands for Automotive Safety Integrity Level, and it's on 4 levels from A to D for each hazardous events based on the classification of severity, exposure, and controllability. Now, the ASIL gives you the measure exactly how dangerous it is, and how much harm a certain hazardous event can have on people, on humans. So this means that higher the ASIL, ASIL D, for example, you need to take certain more strict measures to make sure that that hazardous situation does not occur, or when it occurs, the effects on the humans are minimized as much as possible. The fourth step is to assign a safety goal for each hazardous event with an ASIL. So we define the hazardous event, we calculate its ASIL based on the 3 factors, and we define a safety goal. The safety goal is expressed in terms of functional objectives. So for example, if the hazardous event is unintended deceleration, the safety goal should be phrased avoid unintended deceleration. So we need to avoid a hazardous situation to occur. The fifth and the final step is to verify the HARA. Why? The verification of a war product is to make sure that it complies with its inputs, in this case the item definition, it is complete and consistent. So you need to verify your work. Of course, it's not just one person involved in this hazard analysis and risk assessment. There are many people involved in this, but you need to make sure that you cover to the hazard analysis and risk assessment pretty much everything that was defined in the item definition and the hazardous events that you thought of. So here we have a failure, which is the unintended deceleration on the left side, which is actually a hazard for the vehicle. The vehicle is on the road, and when this malfunction occurs, it poses a risk to the persons which are either in the vehicle or outside the vehicle, but in its proximity. And together, the hazard and the risk put together in this operational situation is the hazardous event. Now, the hazardous and risk assessment is addressing exactly this part. The exposure, it's related to the operational situation, and it goes from E1 to E4. E1 means that you have a low exposure, E4 means that you have a high exposure. It means that you find yourself in a certain operational situation more often than not. E0, it's reserved for a situation where you encounter not so often. Let's say there are highly unusual situations. Second factor is severity, and it goes from S0 to S3. Again, S0 is with the lowest impact, the lowest severity. It means light injuries in case an accident occurs. S3 means serious injuries, probability of death is very high, and it's related to the humans which are involved in this hazardous event. Controllability, again, is related to the humans, and it's also going from C0 to C3. C0 meaning a good controllability. Most of the drivers are able to control the situation in case a hazardous event occurs. And C3, it's the lowest controllability. It means that you're either very lucky or you're a professional driver and you are able to avoid an accident when a hazardous situation occurs. When they are put together, they give you the ASIL. Now, these arrows are not to be, let's say, taken to scale, so there I made them like this just to show exactly how serious the situation is. So, for example, ASIL E means that there is a risk, but it's quite low. And as you progress ASIL B, ASIL C to ASIL D, the risk gets more serious. Now, once the hazardous and risk assessment is done, the next point is to define the functional safety concept. When you define the functional safety concept, you start from the safety goal with the assigned ASIL, in this case unintended deceleration or avoid unintended deceleration, and then start to take into consideration the elements of the item. In this situation, I put here the brake ECU, the perception system. So in this situation, the unintended deceleration of the brake ECU was caused by a wrong deceleration request coming from a perception system, so the failure propagated from the perception system to the failure. The functional safety concept should take into consideration the elements of the item as black box and the interfaces between them and what can go wrong, and define measures to avoid the appearance of this malfunction. The next step is to define the technical safety concept. The functional safety concept addresses the what, and the technical safety concept explains the how. How do you plan to do it, to implement? And here we are going in depth. For example, in this situation, we are going in the perception system and we identify all the potential faults that can lead to a wrong deceleration request. And here we're talking about hardware random faults, we are talking about systematic software faults, systematic hardware faults. So, in a nutshell, this is how things are going, from the hazard and risk assessment to the functional safety concept and to the technical safety concept. The ASIL, as you can see, ASIL D, can be encountered in only one situation where severity, controllability, and the exposure, all three factors, have highest values. So you mean that you are in an operational situation that you find yourself more often, and the severity in case of a hazardous events occur is quite high. Serious injuries, death is probable, and it's very difficult to control it. The rest of the situations, if one of the factors improves, let's say, then you will get lower ASILs. QM stands for quality management. It means that it is sufficient if we apply the quality standards. Here I'll give you three examples. In the first example, we have the malfunction of the AB function, no deceleration requests provided when needed. The hazard at the vehicle level is the vehicle does not decelerate automatically when it's supposed to. In the operational situation driving on highway, and the hazardous event is that the vehicle might collide with the vehicle in front or with a vulnerable road user like a cyclist, but since we're on a highway, most likely it is to hit another vehicle. For this situation, we have the probability of exposure 4. Driving on highway occurs more than 10% of the average operating time of the vehicle. We have a severity of 3. Why? Because we're talking about high speeds on the highway, so the consequences of such an event, of an accident, would be life-threatening injuries with survival uncertain. And the controllability in this situation is 0. Why? Because the driver should be always in control of the vehicle and not rely on automated deceleration. This is a little bit counterintuitive, but the Vienna Convention, which is the basis for all traffic regulations in most of the countries in the world, say that the driver should be always in control of the vehicle, which means that no function of the vehicle should replace the driver related to its agency, but rather to help him in some way. Since the controllability is 0, the ASIL, we have no ASIL here, we are in the QM situation, there is no safety goal, and there is no allocation to the item. However, the requirement is to inform the driver in the driver's manual that such a function, like autonomous emergency braking, does not relieve him or her of his or her duties, just provide support in certain situations. We cannot guarantee that such a function will work in all situations. The second example, we're talking about more or less the same situation. We are driving on highway, but in this case we're talking about a deceleration request which is provided when not needed. And the hazardous event is that the vehicle decelerates to standstill and becomes an obstacle on the road and triggers a collision with the following vehicle or the following vehicles. Why? Because the drivers are taken by surprise. Nobody expects that a car will suddenly brake in the middle of the highway with no object, with no obstacle in front. Here the exposure is the same 4, severity is 3. I explained you earlier why, but in this situation the controllability is 3. Why? Because all the drivers are taken by surprise. There is little time to react or no time to react, and thus the drivers are not able to control the situation and avoid the accident. In this situation, since all 3 factors are high, the ASIL is D. The safety goal is that automated deceleration intervention shall be limited such that the ego vehicle does not become an obstacle on the road. So this is why when the AAB is applied, it will decelerate you with maybe 40 or 50 kph, but it will not decelerate until the vehicle is in standstill. Why? Because you as a driver and the drivers of the following vehicles need to have sufficient time to react and to brake themselves, and thus you avoid an accident. The allocation to the item is to the brake ECU. I'm moving to a third example. The malfunction is the same, deceleration request provided when not needed, and the hazard is the same, vehicle decelerates automatically when it's not supposed to, but the operational situation is different. Here we're driving on city street. The hazardous event is the same, vehicle might decelerate to standstill and become an obstacle on the road and trigger a collision with following vehicles or vulnerable road users like motorcycles or bicyclists. Exposure is 4, again, because driving in the city, it's operational situation with high probability. Severity in this situation is 2. Why? Because we are driving at lower speeds. We are talking about 50 kph instead of 120 or 130 kph, the speed which are on highway, if we're not talking about no speed limits. So severe and life-threatening injuries are possible, but survival is probable. Controllability, again, it's not 3, it's 2, because the drivers are taken by surprise, but due to lower speed, they have more time to react and avoid an accident. So if we put together all these 3 factors, we get an ASIL B, and the safety goal would be to avoid deceleration request without a valid object in the collision path. In this case, the allocation is to the perception system, a camera, radar, or a LiDAR. Now, as we finish with the hazard analysis and risk assessment, we move on with the requirements. Actually, the safety goals are the first requirements, and as you can see them on the left side. Safety goals are the first requirements and are the inputs to the functional safety concept. In the functional safety concept, as I explained earlier, we define functional safety requirements with the focus on the system architectural design. We need to know what are the elements of the item. We need to know what are the interfaces between them, what kind of information or what kind of, let's say, other physical values are exchanged between those elements. It can be power supplies, and so we're talking about electric energy, not necessarily information. So, having this system architectural design in mind, we define the functional safety requirements in order to prevent the violation of the safety goal. Once the functional safety requirements are defined, we move on to the next step to define the technical safety concept. Technical safety concept can be done at item level, which can be considered as a system on its own, and then it can be further refined in each subsystem that can be considered as a system on its own, like the perception system, the brake ECU, the stability ECU. And each of them can have a technical safety concept, take into consideration their own system architectural design. So the technical safety requirements are derived from the functional safety requirements and should explain how we need to implement those functional safety requirements and make sure that they are not violated and hence violate the safety goal. Based on the technical safety requirements, we build the system architectural design, or we identify in the system architectural design its elements which are safety relevant and define their properties and safety measures and safety mechanisms to make sure that the system architectural design is done correctly. But about architecture a little bit later. A technical safety concept with its technical safety requirements and the system architectural design, it's an input to hardware requirements, hardware safety requirements, and software safety requirements. So from here we are discussing about how we implement the safety requirements at hardware level, how we build a hardware design in such a way that the safety requirements and the system architectural design are satisfied. And also, we're building the software architecture, which takes into consideration both safety and non-safety requirements, and then software unit design. Hardware safety requirements and software safety requirements are connected between them through the hardware-software interface. This means that the hardware elements need software to configure them, or they need software intervention in some way, calibration, configuration, or if software needs hardware support, for example, a memory protection unit in case freedom from interference is needed, then hardware-software interface is the medium through which hardware and software communicates the needs to each other. The functional and technical safety concepts start at an item level and continue on the system level, and ASIL should be inherited throughout the entire thread. So from left to right, if you're reading and you're seeing the arrows, ASIL should be inherited, unless we're doing ASIL decomposition at some point in time. But it's not in the scope of this webinar to discuss about ASIL decomposition, and we assume here that the ASIL is the same and will be carried out through the entire derivation of requirements. This means that when you are building software safety requirements, for example, and you do not have yet the technical safety requirements, you should not assign the ASIL based on your own experience. You should wait to have inputs from the technical safety concept or not. You might not have such inputs, and then you decide if it's a QM or an ASIL requirement. So the scope of the safety requirements at all levels is to define or refine the safety measure, mechanisms, and strategies so the safety goals are not violated, or the safety goal is not violated. What I learned from my experience so far is that you need to keep the requirements as simple as possible, but avoid being too abstract. This happened to me a lot because I defined requirements in the technical safety concept, and when discussing them with hardware and software, they come to me and say, I don't understand what you exactly mean here. So I try to to write requirements that are easily readable. They express exactly what I wanted and can be easily understood by them. When writing requirements, think about how they can be validated. In this situation, I mean tested at that level. So you should have testable requirements. If it shouldn't be each requirement should be tested with a separate test case. You can bundle them together, but they need to be testable. You should avoid having too many non-functional requirements. Have as many functional requirements, because a physical test, is better than having them only treated by review or by documentation. Cross-check safety and non-safety requirements because they don't need to contradict each other or overlap. It might happen that sometimes non-safety requirements are mentioning the same thing as safety requirements. So you need to discuss with the system architect or the system requirements engineer or with the hardware or software requirements engineer and make sure that these requirements do not contradict each other or overlap. One of the most important advices that I would give is do not start implementation before having the requirements. This happens a lot in order to save time. You need to do this only when you are very sure about what you implement and you have a great experience with this. Otherwise, please wait until the requirements are defined, because otherwise you will develop something. Whoever writes the requirement may want different things, and then there is always a fight between you as an implementer and the person who defines requirements if you do the extra work or not. So please make sure or communicate with the person who defines the requirements and say, my plan is to start with this implementation, so please make sure to provide me requirements for this part. Understanding of the requirements should be aligned between the person who wrote them and the one or the ones that are assigned to implement them or to test them. Why? As I mentioned before, it's a little bit hard for other persons to understand, not because you're talking different languages, but because usually they have a different approach. You're thinking things in a certain manner. The persons who are doing the implementation or the testing have their own background, their own way of thinking, and sometimes these two are not aligned. So you need to have discussions and make sure that each other understand the purpose of the requirement and what needs to be done. Always check the correct and complete coverage of each requirement at the next level. Most people stop when their requirement is approved, and they don't want to go to have discussions with the next person. They just rely on them to make sure that they cover the requirement completely. No, it's not doing micromanagement. It's actually making good engineering sense to discuss with each other. Again, it's related to the same thing. Maybe they have a different, even if they approve the requirement, maybe they have a different understanding. Make sure that you are aligned. If requirements are changed at any level throughout the project, maybe when everything is mature, let's say, and frozen, you froze the architecture, but you have a change request coming from a customer, or maybe you discovered something, a defect, and you need to do a workaround, make sure that all affected parties are involved in assessing the impact of that change, not only downstream, but also upstream. So for example, if you operate a change in software or in hardware, you also need to discuss with the system level and make sure that they adapt their requirements or make sure that the requirements that are affected on their side are also evaluated from their point of view to make sure that they need to write new requirements or it is sufficient that workaround is at some length in agreement with what they defined originally. This is about requirements, and we're moving on to the architecture. So the architectural design is the cornerstone of the functional safety activities. I would go and say that the architectural design is the cornerstone of any product development, because there you put into practice and you implement actually what the requirements are saying. Requirements are asking something, but they go to a certain length. They cannot build you something. So you need there to build an architectural design. So same way as you're building a house, you need to make sure that you consider everything there, and you make sure that the requirements are not conflicting each other, and you make sure that whatever you are doing, you are choosing, it's actually feasible. So in the architectural design, the concepts, the safety measure, and the safety mechanisms should be put together in a coherent format. When architecture is started at item or system level, it will include both functional and physical architecture. So as long as we are at the item level or system level, we have two architecture, functional and physical, and they should be correlated one with each other. You cannot have a physical architecture without knowing exactly what you want to implement from the functional perspective. There can be many functional architecture because an element is able to implement different functions, And each function at vehicle level can use common physical elements, for example, autonomous emergency braking and adaptive cruise control, because we're talking about here about deceleration in both situations, can have overlapping architectures up to a point, and they make use of the same elements, like perception system, braking system, vehicle stability system. But they have different characteristics. So here you need to, when you build this architecture, to make sure that you arbitrate between different functions. At item level, we go back to the functional architecture, what I defined for autonomous emergency braking. As you can see, on the perception system, the responsibility on the left side, we're talking about sensing the environment and providing either objects or brake requests. The stability system is responsible to provide information to the main ECU about the stability of the vehicle. Maybe the road is wet, and maybe triggering a brake intervention is not the best idea. So it's better not to complicate matters. Of course, the main vehicle ECU is responsible to gather all that information and communicate with all the other functionalities. The steering ECU provides the steering angle. We also have the engine, which provides acceleration and deceleration. We have the driver, which has the control and provides also inputs through the HMI to the vehicle, to this function, right? So they might press the pedal, they might turn the steering wheel, they might press the accelerator pedal, they might turn the signal. So in the end, they can do a lot of stuff, and the driver itself has a certain functionality inside this item. And this is the functional architecture at item level. As you can see, there are two different interfaces. We're talking about information interfaces and intervention interfaces. The information interfaces provides information between the ECUs and are marked with orange, and the blue arrows are pointing out exactly how one function or sub-function intervenes over the other. So the perception system sends a brake request or an object list to the main ECU, and main ECU, once it gathers all the information, sends the brake request to the brake ECU. Here is the physical architecture. Because we're talking about the functional architecture, this functional architecture can be should be done by physical elements. You need physical elements to fulfill this functional architecture. Now here we are, let's say, one-to-one, but it's not necessarily to have this one-on-one allocation of the functions. Sensing the environment is the responsibility of the perception system. Sensing the stability of the vehicle is the responsibility of the stability system, like ESC. The main ECU is responsible to gather all the information. The brake ECU is the actuator. The brake system is the actuator. We have the steering. ECU. We have the engine, which provides the acceleration and deceleration of the vehicle. We have the driver, which provides controls, inputs, activation of the function, deactivation of the function, and different intervention on the dynamic of the vehicle. And we have the HMI, which is on the bottom left corner, which is the medium between driver and the vehicle, and is responsible of transmitting information from the driver to the other elements. Moving on to the system level. So here I took as an example the perception system. The functional architecture at the system level gets a little bit more refined. So the responsibility of the perception system is to sense the environment, to see exactly where the vehicle is, what are the surroundings of the vehicle, the road infrastructure, other vehicles, other persons. So this happens through the environmental feedback to the environmental perception system. The environmental perception sends raw information to a function which deals with objects identification. The algorithm that happens inside is quite complex. We will see a little bit later some representation of it. The objects identification function sends the object list to the intervention generation, which receives other information from the other ECUs like velocity, yaw rate, basically the vehicle dynamics, and sends a collision warning and or a brake request. The bottom part is dotted because is dashed because this is not applicable to all perception systems. This is not applicable for a camera. The camera just sends the environment, but is applicable for radars and lidars, which need to send a scan pattern on the environment and then receive feedback from the environmental perception. If you need the scan pattern, you need to calculate the environmental scan pattern, you need a frequency, you need to make sure where you are sending the scan, maybe horizontally, vertically. Then you send the scan pattern to the environmental scanning element, which need to be synchronized with the environmental perception, because you need to know when you send a scan pattern to scan the environment and make sure that after a certain period of time you'll receive feedback, and then correlate these two. Now, this functional architecture is assigned to the following physical architecture elements. The environmental perception part, which receives the environmental feedback, it's assigned to the receptor. Receptor, it can be a radar antenna or an imager in case of the camera. The environmental scanning is done through an emitter, radar waves generator, for example, or a LiDAR pulse, which scans the environment. Again, the synchronization. Now, the scan pattern and the raw information come from a processing element. So, basically, the object identification, intervention generation, calculation of the environmental scan pattern take place inside the processing element, because it is the most complex one. The processing element communicates with the vehicle through a communication physical interface, and it sends the information. For example, the collision warning and or brake request, sends it to this communication physical interface through the vehicle. I follow the same logic, so with blue arrows I marked the exchange of information, while with orange I marked in this case, the power lines. So you see that the power supply, you need a power supply to supply the communication physical interface, the processing element or the receptor, and of course with the dash part, also the emitter if it is the case. You need to supply them with electrical energy in order for them to work. Now, we have functional and physical architecture at item level and at system level. And this is where functional and physical architecture part ways. Functional architecture is then further detailed at software level. Here I took the object's identification and I split it into more sub-functions. Please do not take this as a, let's say, one-to-one representation of an object identification. It can be more complex than this. But just to have an idea how it works, you have the raw information as an input to a noise filtering unit. You need to make sure that what you are sending, the filtered information, is actually there are valid objects or reflections from the environment, so you eliminate the noise. And then with complex algorithm you detect peaks corresponding to real-life objects. Moving on, you send this relevant information to object list generation, where the object list basically selects whatever is, according to some rules, whatever is important. For example, nearby vehicles or road infrastructure, to make sure that you are not on a collision path with it, because we're talking about autonomous emergency braking, and then sends this object list to the intervention generation to make sure that it processes the objects together with the vehicle dynamics, and then it decides if we're in a dangerous situation or not, and triggers a collision warning or a brake intervention if needed. Now, all these sub-functions should be monitored. So what is safety relevant here? Each of them, each of the sub-functions are monitored for input and output data checks. So you need to make sure that whatever is there, it's actually within range, for example, or it's not delayed, just to give you a few examples. And then you analyze this input and output data, and if everything is okay, data is in range, it was not corrupted, is not delayed, it's not implausible, then you give it, you don't do anything, you let the algorithms to work by themselves. If the check results detect that something is faulty, you send it to the error handling, and the error handling takes a decision to send a fault notification and degrade the functionality that is problematic, so on and so on. Now, about the physical architecture, at hardware level, I choose the power supply. The power supply, it was represented only by one block, but it can be composed of different hardware elements. So the input to the power supply of any system is the system input voltage, which can be, for example, from the battery, usually it's from the vehicle battery. That voltage is filtered, and the filtered input voltage is input to the main power supply. The main power supply will output, here I put only one voltage, but you can have 1, 2, 3, how many voltages you need. And of course, if the main power supply is not capable of supplying all the elements, or all the hardware elements, which is usually the case, you will need maybe a secondary or a third power supply. So these are optional, but usually this is the situation. You have a main power supply, and then you have secondary or tertiary power supplies that supply, for example, the front end, the receptor, the emitter, memories, or imager, for example. A crucial element when you're doing the architectural design are safety analysis. So most people say that safety analysis or see safety analysis as disconnected from the architectural design, is something that is needed, is requested by the standard, but that doesn't necessarily see the connection with the architectural design. Well, the safety analyses are used to support and to verify the architectural design. Once you do the safety analysis, which should be started together with the activities for architectural design, not after the activities are finished, you need to identify potential design weaknesses. I know that everyone thinks that they are sufficiently experienced and they can build an architectural design which is flawless, but nevertheless, from time to time, you can find weaknesses when you expect the least. Potential systematic faults, you detect them through qualitative analysis, for example, FMEA, and you use it at all levels, at system, hardware, and software levels to detect if there are systematic faults. If you detect systematic faults, you need to do something. An example of a systematic fault is, let's say, at software level could be forgetting to initialize a variable and using that variable as a divisor. And then you divide by it, and of course, the first instance is 0. So you divide by 0, and each time you go through that software loop, you will have division by 0 and thus an error. So this is a systematic fault. At hardware level would be to use underdimensioned hardware element. So for example, a power supply that is not capable of supplying all the elements. Maybe you need 5 watts and you choose a component which is capable of providing only 4 watts. And when you need those 5 watts the most, you are, let's say, not available because you forget to dimension it properly. At software level, safety analysis and dependent failure analysis are done according to the software architectural design and can follow the functional and/or processing chains, considering both static and dynamic aspects of the software. Now that I mentioned the dependent failure analysis, this is an almost overlooked analysis. Usually it's, let's say, more or less easily dismissed. It's more focused on hardware and software usually, but it should be done also at system level, and is chosen only when freedom from interference is needed or ASIL decomposition is done. Now, if any of those are not requested, usually the DFA, as it is shortened, the dependent failure analysis, is overlooked. The problem is that even if you don't do it, and if you have, for example, ASIL B component and an ASIL B monitor, you can do the design in such a way and both of them be affected by a common cause fault. Why? Because, for example, you can decide to monitor the input voltage of the MCU through software, through ADCs, which are located on the MCU itself. So this means that when you're in under or an over voltage condition, so voltage out of range, the MCU is not able to operate properly, and then the software again, the software itself is faulty, and the monitor will not operate as it should be, and of course you will not be able to detect the voltage out of range. So this is, for example, a dependency between the monitor and the monitored element. So you need to take into consideration, even if you don't need freedom from interference or ASIL decomposition. Make sure that you don't have unintended dependencies. To prove that the hardware architectural design is able to cope with the random hardware faults, a quantitative safety analysis, FMEDA, is done. Of course, here I need to make a statement. I'm talking about ASIL B systems, because this is where my experience is. So for ASIL C and ASIL D, you also need to perform qualitative and or quantitative FTA. So here I'm talking about ASIL B system. So to sum it up, you do qualitative analysis at system hardware software level, you need to do dependent failure analysis where is due, and you need to do quantitative safety analysis, FMEDA, starting from ASIL B onwards. Verification. Verification is easy. The objective of verification is to ensure that the work products comply with their requirements. So you have the requirements, you have the architecture, you have the implementation. Now you need to verify one against the other. You need to make sure that it's based on the three pillars. You need to ensure that it's correct, complete, and consistent. This is what is ensured through verification. Now, verification can be done through testing, and verification can be done through reviews. If you are building documents, if you are building work products which are documentation, you need, or test reports or analysis reports, you need to verify if they contain all the necessary information to prove that you reach the desired ASIL. If we're talking about the implementation itself, you need to have test cases. You need to have tests, physical tests, that you need to ensure at hardware, software, system, vehicle level that you do not violate the safety goal. The essential elements to ensure the complete verification are the methods for verification, for example, requirements-based tests, right? You have the requirements, and then based on those requirements, you build tests. Methods to derive the test cases, for example, from the analysis of requirements. You can decide, this is why I said earlier during the requirements chapter, that you need to make sure that the requirements are testable, are verifiable. And the test environment, which can be hardware in the loop, software in the loop, or it can be the vehicle. Documents can be verified against requirements through reviews. As I mentioned, this is valid for the documents that you build to make sure that they are complete and contain all the information that is needed to make sure that you prove that you finish the safety analysis is consistent with the architecture, there are no weaknesses, whatever you found in the safety analysis, for example, is implemented in the architectural design, and then you have these kinds of reviews to make sure that these are implemented. Moving on to safety culture. Here I will not cite from the standard, but I will say from my experience again, no one can expect an employee will gain competency in functional safety just by participating in mostly abstract trainings. I used to give such training, and I think also this one is a little bit abstract. I tried to be more eloquent, but yeah, let's see in the end how it went. But the employee needs to understand exactly how the functional safety is embedded in their responsibilities and daily activities. So it should be mentioned in their in the procedures, in what they are doing. They should be trained. They should be explained exactly what are they doing and how they are doing things, how they can affect functional safety, or what they are doing to ensure functional safety. Because usually it's the things are phrased, what do you do to impact functional safety? But it's not only impacting functional safety, but rather we're talking about how to ensure functional safety. And usually it's more easier than it looks like. So functional safety is not just some kind of witchcraft. Basically, if you follow good engineering standards and you think about your work, to do your work fine according to what you learned, then it's sufficient, and then functional safety is ensured. Now, most of the times you encounter slogans saying safety first, quality first, customer first, money first, everything is first here. And this can be a little bit unnerving, because you need to understand exactly what needs to be first and when, because nobody says, okay, you need first here. No, everything is important here. Quality is important. You need a good quality of a product, you need the safety of the product, you need to satisfy the customer, you need to fall in the budget. But you need to understand that the strategy needs to be done in such a way that all of these factors do not counter each other. You don't need to choose between safety and quality, for example. They both need to be ensured, and the customer needs to be satisfied and then by ensuring the quality and the safety according to their requirements. Of course, you need to follow a budget. You cannot overspend, but usually you need to make sure that if they are in the conflict, of course, something is wrong at some point, and probably there were some bad decisions. If there weren't bad decisions, probably there is a gap, and this needs to be fixed in the process. But usually, each of them is important. In a normal situation, all elements, as I said, are combined and should not conflict each other. I mentioned before, and you saw the QM and the ASIL. Functional safety relies on a good quality process being implemented, hence the QM. So we rely on the quality. If quality doesn't exist, you cannot talk about implementation of functional safety. Cost can be tailored only if there is enough confidence that the end result is not affected in terms of quality and safety. So yes, you can reuse good practices, you can reuse resources, you can reuse whatever you developed before. You don't need to reinvent the wheel each time you are going into a project, but you need to tailor the budget in such a way that quality and safety are ensured. And if the customer wants something that is in strict violation of the safety standard or quality standard, they should be reminded that there are repercussions if quality and safety are botched, and no one should accept any customer requirement or change request if the responsibility is not clear, and the customer should be reminded that they are responsible, because if you are doing something at the pressure of the customer, then you are responsible if anything goes wrong. So the customer should be reminded, yes, there are deadlines, but nevertheless, you need to follow quality and safety. Documentation is not just a burden. It's a proof of you doing the things the right way. It also helps you or others later to understand what was done, how, and most important, why. This is critical in complex systems. It happened a lot that we took some decision in projects, and then a month, 2, 3 afterwards, we didn't recall exactly the entire discussion or how we ended up with the results if it wasn't documented. But if you note down the steps and why you reach a certain conclusion and you implemented some stuff, then it is easier for everyone. And it saves time in the end, later on. Rely on others to review your work. They might find gaps that you cannot find because you are subjective. So this is like trying to tickle yourself. You will not be able to do that because you know exactly what's coming. So you have a bias against what you did, and you should rely on others to review your work. Do not get upset if you think you did a flawless job and they come and redline everything that you've done, and you need to come back and redo some stuff, because they might have a point, and you learn from these situations, and in the future you will not repeat the same mistakes. And you should remember the little things, if ignored, can lead to system breakdown. You cannot imagine how a minor software glitch can lead to big issues at vehicle level, but this is happening. Just check whenever you see in the press that there are recall campaigns for different manufacturers. Just check exactly why they are doing this, and you will see that there is a minor issue with that, maybe with a certain part, maybe with the software. So you need to they need to recall the vehicles and do minor changes, or maybe a complete overhaul, and bring a software patch, for example, because they need to fix something. So little things, usually you cannot go over them, because little things will lead to the system breakdown. Now we're going to Q&A. So we have some questions here. How do you apply SOTIF in your development? Well, this is a good question, and this would be a topic for another webinar. And SOTIF itself is a more extensive subject, so it's not just to be treated in one question. I'll either treat it in the webinar or in a podcast. So SOTIF is very important because it relies on external factors influencing the performance of your functions and in the end leading to the violation of the safety goal other than what is treated in the functional safety standard. So it's complementary to the functional safety standard. And for the perception systems, usually are there, let's say, weak spots, like for cameras getting blinded by the sunlight, or the radars in when we are talking about radar interference, because nowadays most vehicles have radars, so you will encounter radar interference in operational use cases. Or maybe when there is a lot of metallic infrastructure. So SOTIF will be a topic for a podcast. Thank you for asking these questions. I'll think about it and I'll develop it later in a podcast, and I will let you know when we have the podcast on this topic. If there are another question, if there are different standards in place for autonomous driving cars. I mentioned in the beginning that standards usually come from the experience of people in the field. So you can have a first edition of a standard which relies on an existing standard, and then as soon as the field evolves more and more, you have more lessons learned and the standard are more coherent. So right now, as far as I know, there is a UL standard developed in the United States because they are testing extensively autonomous driving in San Francisco, for example. So they are building on that. But a first edition, I think it appears this year, but we don't have anything yet at international level. So there isn't yet an ISO standard for this. Probably it will we'll have a first edition, and then we will, when autonomous driving will become used at a larger scale, probably we'll have a more coherent standard. Even the functional safety standard, we are only at the second edition. First edition appeared in 2011, and the automotive industry is at least a century old. So we are there in the making. There are different standards. SOTIF, for example, SOTIF didn't exist until recently, although these issues existed even for some years when the ADAS systems became more and more used in the vehicles. In case we decompose ASIL into two different ASILs, or ASIL plus QM, how then to distinguish which of them should be responsible for monitoring and which should be responsible for performing the function? So this is a good question. Usually when you do the decomposition, you need to make sure that you have redundancy, or that the function and the monitor are independent. So of course you do the analysis, but you can judge from the beginning. I'll give you an example. We have the communication physical interface, be it CAN or Ethernet. The hardware component can be decomposed as being QM out of B, and we have the ASIL B of B on the monitor. So we should have always on the monitor side, we should keep the ASIL, because it should be capable of detecting the faults. But of course, the function should be simple enough. So in this case, the function of a communication component is to send information. So if we're talking about more complex functionalities, maybe ASIL decomposition shouldn't be applied. Okay, another question. Can you give me a brief about hardware section and analysis part and fit rates and how it relates to ASIL? This should be another topic as SOTIF for a podcast. I assume that we're talking about FMEDA here. Here the standard provides an indication. For example, for ASIL B, the fit rate which is allowed is 100. So this means one fault in 10 to minus 9 hours of driving. For ASIL C and ASIL D, we have 10 feet. So these are from the standard, but things are not just, let's say, easy, because you cannot just put fit rate on a component and then say, okay, this fit rate and this fit rate, we just sum them up together and we will have the final fit rate. So you need to take into consideration how to properly balance safety mechanisms in order to ensure the right fit rate. But thank you about these questions, and thank you very much for attending this webinar. It was a pleasure for me to share from my experience, and I want to say to you that please follow Spirasoft on social media, because we'll come back with more interesting webinars and podcasts.